Well, thanks everyone for coming here today. So I'm Brian Law. I'm a specialist solution architect at Databricks. And then my background prior to Databricks was working in data science and machine learning at various corporations where I worked on different use cases from standard tabular analysis all the way through to working with real-time video as well and a bit of natural language processing. So today the agenda is I'm going to focus at least code-wise from a PyTorch perspective. That's just the framework that I've been using lately the most. But then a lot of the concepts that we're going to talk about today will extend to TensorFlow, MXNet, and PyTorch as well. So firstly, we'll go through, talk a little bit about the ecosystem and what actually happens when you're building a deep learning job and how the code all works. And then we'll go through some notebooks to show some of these principles in action, and then hopefully give you some ideas on how you might approach your projects, how you might best utilize the resources that you have available. So unlike some of my customers, you don't come back after leaving your cluster on all night to find that it crashed 15 minutes in, and then you're just paying for 8 GPUs to run. So firstly, this talk is not going to be about ideas and use cases and how we tackle that from a deep learning perspective. I'm not going to go in depth into any particular major areas, though the example will be a computer vision one. And then this is not talking about state-of-the-art models and trends. There are a lot of different ideas and different frameworks and different ways that you can tackle those problems, but this is going to be about how you go through, train a network, make efficient use of resources, and hopefully get some good results at the end. So although I do train a network, and there will be like targets and everything, I haven't really optimized it for producing like best accuracy, for example. This is more looking at the process and the scaling. So today the focus will be a bit about the hardware side of things. We'll talk a little bit about understanding profiles so that you know where your bottlenecks are, and then we'll talk a little bit about how we scale up with distributed compute. And then, given this only like 35 minutes, so can't cover everything, but we'll go through maybe some of the areas where I'm seeing future development coming now, and then happy to take some questions at the end as well. So that's the agenda. So firstly, just when would you actually use deep learning? So there are some sort of slam dunk cases where you would go to deep learning. Examples including computer vision. So all those, that dog there is actually generated by one of Google's new generative networks, where you just type in a text description and get an image. And probably another common one is natural language processing. But I guess if you're at the session next door just before, you can see that increasingly deep learning is coming into the tabular space as well. So time series, one that was covered just before. Another interesting area that's coming up is graph neural networks a bit. So things like understanding supply chain, understanding relationships between different entities. And then also recommender systems are slowly sort of starting to get leverage with deep neural nets as well. So why do we want to scale deep learning? So firstly, a lot of the performance gains have come from being able to scale up deep learning algorithms, being able to put more data through it, being able to put more complicated networks to apply it. And then over time, as we've gotten access to more compute, that's actually probably contributed as much to unlocking all the new networks that we've seen, all the new successes in terms of things like self-driving cars. That's all about scale, all about compute. So if you go back to the basics, then the first sort of neural network perceptron and the first sort of methods of stacking them up and putting them all together still very much apply. I don't think that's moved very far. But it's now that we can do it at scale. And as training these networks takes a long time. So actually I think this one finished just today, or it'll finish in the next 2 or 3 days. So this is a 175 billion neuron network. And you can see from that screen grab there that it's just been training at about 1% per day. And then it's being trained on hundreds of GPUs at the same time. So this one was 3 to 4 months with 400 plus GPUs and yeah, only 1% per day. So that's why you want to be able to write code that's efficient, that can scale up so that you can get your results faster. Because what I've seen with machine learning projects is it's not so much about finding the perfect model and getting the perfect results. It's the amount of experimentation you can do, the number of cycles you can go through to test different hypotheses. And especially with neural networks, given how long it takes to train, then it means that your cycles are really slow and your opportunity of delivering results on a tight timeline are quite limited. So firstly, let's talk a bit about the hardware. So originally, everything was trained on CPUs, and they're very good generalist processors. But then, especially with deep neural networks, GPUs give you significant speed bump. It's really good at the massive parallel calculations that are needed. And this is just a quick chart of the difference in training time and the difference in training cost for CPU versus GPU. Now, I know Intel has been working on new instruction sets to try and make it more efficient, but as of now, it's still a pretty big performance margin between CPUs and GPUs. Probably your biggest limitation factor actually is more availability of GPUs now. Working with some customers in some AWS regions, then we might, you think you can just start things in 3 to 5 minutes like a standard Databricks cluster, but then you hit up the insufficient resources error message, and then you might spend the next hour trying to start your cluster up properly. So hot tip, I guess, if you're doing overnight trading, then it seems like everyone likes to fire things up around maybe the 10, 15 minutes around midnight. So if you start your things up a bit earlier than then, and you've got a on-demand instance, then hopefully you can keep your compute and get your model trained. So normal models take time too. So before I talked about that massive language model, and I'm guessing nobody here will be training those, at least on cloud resources. If you are, do come up, we can have a chat and see how we can make that happen. But even sort of more respectable networks that you would use day to day still take quite an effort to train. So ResNet 50, quite a common visual backbone that's used in all sorts of algorithms now. And then that's about 20 minutes on 128 GPUs. Now this is the full ImageNet data set, which is quite massive and is probably much bigger than the types of data that you would have available for your specific use case, but it gives you an idea and a sense of scale. On the natural language processing side, then, BERT large was 4 days to train on 64 GPUs, and that type of model is what you might be looking at in order to fine-tune on your particular use case and to build a prototype out. So there are a few key factors that determine how big you can scale and how well it's going to scale. There's the hardware config and the node selection. There's the methodology which you scale it, and then finally algorithms as well. Now today we'll talk more around hardware config and nodes and a bit about scaling methodologies. We won't really cover the algorithm part, so there are new libraries out there that can help you optimize on the network side as well. But what I've noticed is that it seems to be, it's a bit more handcrafted, specific to the type of network. It's not really a general technique that you can just blanket apply. So firstly, in order to understand scaling, we have to understand all the steps and how it all fits together. So there's the code portion, and then there's also what's actually happening on the hardware level, because all our bottlenecks are going to start popping up mostly on the hardware level, and then it's about how we can adapt things to make it work better. So you would have your raw data. That could be images, that could be a database table if it's like natural language processing, and then generally there'll be a data loader step. So the problem is that you don't have enough memory. So then the data loader will be the function that's responsible for picking up the raw data and feeding it into the network. Now, because generally you can't feed the whole data set, unlike say with tabular data, then you also have to break it up into chunks. So then there's a batching process. Then finally, we have the two-step process in the model training, so the forward and the backward pass, and then the updating of the actual model weights. On the hardware side, then when you're training on Databricks, you'd start off with the data in the object store. Then there's the connection up to the instance, so these kind of problems are generally quite hard to diagnose. I think Azure, for instance, has like an actual, I think, physical data rate limit between the connection between the instance and the object store, but it's not really documented and you don't really know when you've hit it. Then afterwards, when the data's gone through into your compute instance, next step is the CPU side, which will do some of the munging of the data, some of the transformations, and then finally to the GPU compute. So the goal, in order for us to be able to train networks quickly and cheaply, is firstly to try and max out our GPU consumption. That's the most expensive component in this. And then to get through the training epoch as fast as possible. So one epoch is a full loop through the data. And then for training, I guess, actual deployment models, you might be looking at 50, 100, 200 epochs that you'll want to go through. So first step, let's talk a little bit about hardware. So on the hardware side, as I said, you start off with the object store, then you've got the transition into the compute instances, then we've got the CPU and the GPU compute. So the main things that play a key part in this is on the RAM side of things. So typically GPUs have a lot less RAM than CPUs. Now I think the latest A100 chips do come with significant amounts of GPU RAM, but then I think there are only like 1 or 2 regions on Azure and AWS and GCP that have them, and they're pretty expensive as well from an hourly cost basis. So generally you'd work with, like for AWS, maybe a G4 instance might be a good one to start off with, and then there you've got much lower limits on the amount of GPU RAM you've got access to. So as I said, we've got plentiful CPU RAM, but we don't have enough GPU RAM. And GPU's RAM is where all the data's got to end up, where the model's got to end up. So then, because you've got large data sets, you end up with that transfer between CPU and GPU RAM. And that's one of the key bottlenecks that arises as you try and scale up your model. So then if we think back to the code side of things, your data loader and your data pre-processing generally happens on the CPU side of things, and then the actual model calculations happen on the GPU side of things. And so what happens when we scale up? So we scale up by adding more GPUs. Now each GPU is kind of a discrete card. In some instances, there might be like special interconnects between them. That's probably more on a node by node type, and you probably need to access like lower level NVIDIA APIs in order to get access to that. So for most problem sets, when you just add more GPUs to try and make it run faster, things that happen is that it adds an extra sync step that needs to happen between the different GPUs. So you will find that you do not get perfect scaling, which is why it's important to focus on making sure that you've done everything you can to make it work well on one GPU, then you can look at steps to add more. So let's talk a little bit about the model scaling paradigm and how that fits together. So there are 2 ways to scale. Data parallel, which is where you've got your big data set and then you break it up and send a portion of the data to each GPU. And then there's the more advanced and experimental model parallel. That's where you're splitting the actual network across GPUs. So generally, we'd probably be in the data parallel space for most applications, unless you're looking specifically at large language models. And this is like a visual explanation of what data parallel is. So we've got our full data set, and then our data loader has taken it and then extracted a small batch. And then from there, that batch gets further broken down into a chunk for each GPU. Then each GPU is going to have a copy of the model. It's going to crunch all the maths for that particular batch. then it'll go back to the data loader to get more data. So with this one, the way we're making it run faster is we're scaling up the batch size. We scale up the batch size, we get more epochs through, but then the thing that slows us back down with this one is that the model weights need to be synced each time across each step. Model parallel is one that's less common. This one is where your model is actually too big to fit onto the GPU. I'd say probably these days, and given the experimental nature for a lot of model parallel frameworks, it's probably better off trying to see if you can get one of the big A100s or something, rather than to actually work on trying to do model parallel properly. So with the model split across GPUs, and then that also means that it's harder to tune as well. And then if you look into a lot of the ways that they tune model parallel, it's actually dependent on the network itself. Because you remember, it's like network's like a giant interconnected graph. So then you've got to decide which chunks am I going to carve off and put on which GPU. And then you need to consider how long it'll take to move data back and forth and sync that as well. All right, so let's go through some code. So firstly, this is that showing up? I'll share the links for all the notebooks and everything anyway. First step here is going to be about working with data. So a lot of the frameworks come with prepackaged data that you can use these days. But then one thing you'll quickly notice is even the simple step of just downloading the data set, unpacking it onto the object store can be quite a time-consuming process. So what I've got here is one pattern and the way that you can approach this. So in this notebook, what we're doing is we're going to go through and then create a Python script that's going to do the actual downloading of the data. And then we're going to have that Python script get executed on our cluster when it starts up. So then we'll save all that to the local drive that actually exists in all Databricks nodes. So if you ever go into the shell or you go into a terminal, then you'll find that all Databricks nodes have a local disk 0. So that's direct attached storage on the node. Now, generally, you don't need to do much about that because Spark will handle everything for you, and you don't want to have to worry about losing data if things switch off. But then in the case of unzipping files, then the local disk 0 can be quite useful. So here, what we got, I've got a Torch Vision example here. I'm just loading the data loader, and then that's all that this script does. Hugging Face example. And so the way we get it to run is we set up an init script. For those who don't know, it's generally a bash script that you would code up that gets executed on nodes as they start up. So this init script will go through and run that Python script that I wrote earlier. And then the way we're going to get that to the object store is through a separate copy notebook that I've written. It'll be in the repo, so you can look through that. And that's doing a distributed copy. So it'll use a lot of Spark workers, and then it'll go through and copy all the files across in parallel. So then you'll get the data set unzipped and available within sort of minutes rather than having to wait hours. And in order to make it a bit more simple, then instead of going through the UI, I've defined my cluster in a JSON structure as well. So you can see these from your cluster setup when you go to set up a job. In the UI drop-down boxes, there's a little JSON UI toggle, and then you can toggle that and see what the JSON config for your cluster is. And then I'm going to use the jobs API to go through and trigger the job. So these are some parameterized widgets. If you ever come across those, that's a way to add parameters into your notebook. So then when you trigger the job, you can customize what comes out. So yeah, that's how you can still leverage the standard data loaders and not have to sit around and wait for ages. Now, in a sort of production standpoint, when you've got a proper ingestion framework, then there are different ways that you can tackle that. You might build it into the way that you ingest your data, or you might have different ways of packing out tables so that you don't need to go through this unzipping step. But then I've also worked with other customers where the way they collect data was they work with an outside party that's doing sort of maybe edge device data collection and everything, and then they deliver the results as like a zip file into the object store that then needs to be processed. So that's the data loader side of things. Then so first notebook here is going to be on how we scale on a single node. So with this one, the way I've set up the project is actually using Python modules. So I think a common criticism I hear at times from customers is that they want to work in a more sort of native code-friendly format as opposed to working with lots of notebooks. So with the workspaces in repos, you can do that now. And then you'll see as we go down that all my model definitions are inside of modules that I've got inside my repo, as opposed to notebook format. So one way you could use this as well is maybe you've got a shared team desktop that's got 1 or 2 GPUs, then you can build the modules in there, test them out, then sync them in, and then trigger that through Databricks as well in the cloud. So what I've done is go through a whole set of experiments looking at different ways that we can tune the job and make it run more efficiently. As always, always start with a baseline. This is the baseline run here. I've got everything logged into MLflow as well. So let me see if we can go through, and I'll bring up my machine learning tab, go down into my experiments, and then this first one is the one. So we go down and I'll just expand the run names there. So the very first baseline, we've got down the bottom there, and that's just using all default numbers and everything. Now the problem with that then is we're not making best efficient use of the RAM that we've got available. And on the data loader side, we haven't gone and tuned the workers. So before I was talking about how we get from raw data to data loader to data on the GPU. So data loaders, all of them, I think TensorFlow, Petastorm, if you're using that one, they all have a workers config there. And then you would want to set that to a reasonable number, I guess, based on what node type you have. So then if you've got multi-GPU, you might want to say, so the 4 GPU instances, I believe, has, let's just say it was 100 cores available. So then you might put the data loader at 20, so then you've got some left over for whatever things need doing, and then you've got more data loader threads to pack the data in. And you'll see that just optimizing the single node, which is the bottom set of experiments there, we can get quite good timings up there. But then you'll see that as we add, I think it's, some of the two, like say the 2 workers there, I do have to step up the epochs on that one, which you can see in the epoch number on the right, then you don't really get linear scaling out of this. So it's always important to try and optimize on single GPU first. So I'll just go back to my notebook. So repos, and as you can see, I've got Python modules in here. So if I open, like say the models one there, then that's a standard Python file. And then if I open that one, that's like a standard coding file as opposed to a standard notebook. So I'll just go back across, oops. So what we firstly go through is set up the baseline here. Then in order to get things run faster, we can look at firstly how we optimize the data loader. So optimizing the data loader is by increasing the number of workers that we put on there. Another standard one is to pin memory. So as I said before, one of the key bottlenecks is the transfer of data between CPU and GPU. So pin memory is one setting that lets you have a pre-allocated memory space that will be used for exchanging the data. So then on the hardware level, it doesn't have to reallocate the RAM every time it goes through to copy data back and forth. It's got that sorted. And then also increasing the batch size as well. Now there are limits in how far we can push this. So if I go through and I double the batch again, then it doesn't actually give me double the performance there. So that's how we know we've started to hit the actual limits on the data loader side of things. And then we can go through once we've got our optimized single GPU code and then start adding more GPUs to the mix. So generally I start small. You might not necessarily get the best results like going straight to 8, for example. And running out of time, so I'll just go down to the bottom as well. It's worth noting that the tensor board is pre-baked into Databricks, and it's one of the ways that you'll be able to go through and understand what's actually happening with your models. So in TensorBoard here, then what you can do is you can add the PyTorch profiler into your code. Now you don't want the profiler to be running all the time because then that actually slows everything down as well. But the profiler will go through and help you identify bottlenecks. So then you can see we've got information here on the GPUs that was used in that run. We've got this chart of the execution time and the execution summary. And then if you go down there, it'll give you some performance recommendations for what was happening with your code. And then if we go across, that's just the overview panel. Probably the most important one for tuning and scaling your job is to look at a bit of what's going on the memory side of things. So here you can see the different batches sort of coming in and out. So as we added more and more to the batch size, then it took like more and more time in order for us to load that memory up, run the calculations, flush it for the next one as well. So then I might just go back to my slide deck. So we've gone through, I've got all the notebooks there. You can look at a bit of how we scale up the job, how we add the profiler, and how we work with the tensor board in that one. So a quick guide on things that you should look at and how to approach your project. Firstly, focus on single node, single GPU to start. Don't just like max it out at 4 or 8 or 16. And then play around a bit with the scale. So set your baseline, then go through and start adding to batch size as well. Now, when you're actually training a model, as opposed to me just doing throughput experiments before, you have a metric that you're trying to optimize for. So then it is worth noting that with increasing batch size, then you also need to tune the learning rate for your optimizer to make sure it's learning properly, and also to make sure your model's learning properly as well. So I think it's common, especially when you're productionizing, to use a low learning rate and then to train for a lot of epochs gives you the most stable result. There are sort of algorithms out there that scale the learning rate dynamically throughout the run that you can experiment with as well. But then as you scale the job, you'll need to go through and retune the learning rate for the scale that you're running your experiment at. And then the RAM side is where you'll get most of your bottlenecks. So be sure to experiment with and check your data loaders a lot. So pin memory, num workers, and also one I've added there is floating point 16 as well. So just for background, most neural networks, when you first set them up, are at 32-bit floating point. And modern GPUs have a lot of accelerated core, especially for FP16 compute. So it's an easy way to get a bit of a performance boost out of that one. And then generally, well, given the amount of numbers being crunched and everything like that, then it doesn't matter that you're losing precision. You know, you're not calculating people's bank balances or anything. You're trying to like classify what an image is, or you're trying to get a bot to speak back to you. That's the link to the GitHub that I've shared there. And I guess a little bit of talk about where things are heading. So before we talk about raw data through to the data loader, through to the batch, and finally the model training process. So one way to look at things is to look at optimizing the data format. So ones that I've seen pop up recently is sort of web data set, and just the last couple of months, there's the FFCV package as well. Now, FFCV is purely for computer vision at this stage. It doesn't support natural language processing, but then it does show some quite promising results in terms of speeding up the model training process. Data loader side of things is about accelerating calculations. So then specifically for sort of computer vision, there's NVIDIA's DALI loader, which uses GPU acceleration in order to load the data through faster and apply the transforms faster. Now, there's like two sides of that coin, because then if you're dedicating GPU compute to doing data transformations, that means you're using GPU RAM for doing that as well. So then your batch size will have to drop back down. So it's probably a bit of tuning to see what works best. And my criticism, I think, of the NVIDIA side of things is they always like to come up with a new API that doesn't align with anything for all the libraries that they write. So you can't just easily port your existing code across with that one as well. Finally, algorithm side we didn't really go into today, but two that I've seen quite recently that show a bit of promise. One is Mosaic ML's Composer module. So that's going through and taking the latest research from papers on how to make a code more efficient, get similar results with sort of less parameters inside the model, but then it's tuned for specific networks. So you can't just throw that at any arbitrary network and expect good results. And then there's also deep sparse, which is also about tuning and cutting down the number of parameters as well. But I think the focus area for the deep sparse engine is more on the inference side of things. So hopefully that gave you a good idea of how it all fits together in terms of training and scaling your deep learning neural networks. Oh, thanks everyone.